We are back once again. LeetCode day 29. It is July 13, and we are ready to perform, I think. Making good progress through the GRIND75. I mean, we have a lot of problems done. Not gonna lie, I started feeling myself just a little bit. Okay, between problems 2 and 10, I think we solved almost all of these like just back to back to back. So that one was a bit of a feel strong, man. I mean, it always feels good when the efforts of your laborers or the seeds, or I guess it always feels good when you can. I mean, it feels the best, right? When you sow seeds for a tree you will never enjoy the fruit of. It feels even better though when you sow the seeds for a tree and you actually get to taste the fruit. And so we got to taste the fruit. I mean, it was nice to be able to do these problems back to back to back. Nice confidence boost. Tried another problem the other day. Actually, it was last night or something like that. And it was a different problem. It was about, what was it about? I have to pull it up. But it was called merge accounts. Okay, and this problem is a different breed of problem. Okay, if you see this problem, run. I mean, only the best of the best. I mean, this is like you watch anime. This is a Big Mom level threat or a Gear 7 Luffy level threat. You want to avoid this at all costs. That being said, in the future we will fry this problem, but it's just a ramp up time. It's the development arc, so gotta keep getting better. Gotta keep putting the reps in. Also fried this lowest common ancestor problem. This was also very satisfying to solve. I mean, always feels good when that works out. Initially, it was a little confusing because I thought I understood the problem. I didn't understand the problem, and I guess that goes to show that one of the most important things, right, is that make sure you understand the problem. And I think that's just a metaphor for life in general. Probably understanding the problem before you even start fixing it is probably way to fix most problems, probably, right? So in the future, takeaway from doing this problem, slow down, read the problem, make sure you understand it, right? Because if you don't understand it, then you might be solving for pretty much an erroneous case, or you might be running with erroneous assumptions. That's always a disaster. Another thing I noticed with these sorts of problems is that, especially when you get to medium or hard, not double checking your assumptions wastes a lot of time. So if you don't double check your assumptions, you might end up in a hard or a medium, 30 minutes in, having a brain blast, and then you're like, oh man, I wasted my time, right? So that is not Flames. Experienced that also yesterday, just not a Flames feeling, right? But more to be done. I'd like to finish the GRIND75. I think we're starting to accelerate, right? And I think one of the most fun parts about this whole thing, and I think there's just probably just a metaphor for hard work. And I wouldn't even say I'm working that hard, but there's probably just something about doing something, right? Barely seeing the bar move day to day, right? But then comparing it to before, right? That's really cool, because I remember when I first started LeetCode, I couldn't solve, any problem. I mean, now we solve 12, right? And just being able to solve 12 is just a gift in and of itself, right? And that's a gift that keeps on giving, right? And every time I look back, I'm just like, dang, like you couldn't even solve one problem. Now you can solve 12. That's always, it feels good. And so, yeah, so I'd like to be able to finish all these problems, right? And then at the end of the day, the goal is to finish all the problems on LeetCode. From there, I think it's kind of arbitrary goal, but it's just something to focus on. I think that's cool. Once we finish it, that would be cool. Move on to the next thing. But as a goal for right now, it's something I'm excited to run towards. So, and I think it's important to have something like that. So, that being said, enough talking, enough procrastinating. Make sure to join the Hyperbolic Coding Chamber Discord. Thousands upon thousands of people joining every single day. We're getting insider tips and tricks. The creators of LeetCode are literally giving away like specific lines of code. If you write this line of, if you print a specific code, if you console.log a specific string, it automatically passes. And I mean, yeah, you can't beat that, right? And the interviewer's not going to know, because let's be honest, they also don't know how to solve the problem. So you're going to want to hop in the Discord and get that code. So just saying, very useful code. That being said, we have 1 hour and 30 minutes on the clock as per usual. We'll try our best here. And feeling good, so I'm thinking 50 minutes of, actually thinking like 50. I'm actually thinking new, old, new, old, new, old. I think that's a better way to go. Notice at the end with the old problems, I've kind of struggled to maintain interest, but I think that might be the best way. I talked about getting into form before with practice, but I think for me, what might work is new, old, new, old, new, old. That way I can kind of work off the executive function I get from doing a new problem into an old problem. Because it's honestly, I think most of us, I mean, everyone today probably struggles with this, but there's just something difficult about being able to withstand mundanity. So sometimes doing a problem I've seen before can be like that, but you know, part of the challenge is just staying locked in. So we're gonna try new, old, new, old, new, old. That being said, we're just doing problems, so we'll start with balanced binary tree, and then we'll go into an older problem, and so on and so forth. So let us do that. So starting the problems, let's do it. Balanced binary tree. So if function is balanced, we're given a root node and we're returning a boolean, already giving recursive vibes. Given a binary tree, determine if it is height balanced. For this problem, a height balanced tree is defined as a binary tree in which the left and right subtrees, so binary tree, this is a binary tree in which the left and right subtrees of every node differ in height by no more than 1. Left and right subtrees of every node differ in height by no more than 1. Left and right subtrees of every node, so every node including 9, 20, 15, and 17, differ in height by no more than 1. So that's interesting. So I guess maybe it's saying that 9 and 20, right? 20 has a depth of 3, right? But 9 has a depth of 2, which is okay. But if you go here, right, 2 has a depth of actually 3, and this 2 only has a depth of 2. So that is unacceptable. Number of nodes in the range is up to 0 to 5,000. So we'll just start, right, if not root, we'll just return. You know, should it be balanced if it's empty, right? And the problem doesn't really specify, so we're just going to say return true, right? We'll assume that it is balanced. Where should we go from here, though? I'm a little iffy on the definition of a balanced binary tree. I think my original one makes sense, but I want to honor my assumptions. We have 3 and 9, 20 and 7. And the difference here, 1, 2, 3, 4, 2, 3, 4. So what actually serves as height balance here? If we assume that for a left and right subtree, 9 and 20, we want to make sure that they don't differ by more than 1, right? Then one way we could do that, and this would be almost n to the n time, unfortunately, but we could do a breadth first search through, right, 3, 9, 20, and for each, you know, 2 nodes, we could make sure that they don't differ by more than 1 by continually going deeper. But for each node, we would actually count how many, we'd actually just count the height, right? Going down and make sure it's not different from the other version. So let's just say we did it that way. So our breadth first search would start at 1, then we go 2 and 2, right? And for both these nodes, we would calculate the depth. Depth here would be 1. Depth here would be 1, 2, 3. That's greater than each other. So we would just return false, right? And then for here, we'd have a depth of 1. and then here we'd have a depth of 2, so that's okay. So if that is the case, yeah, so what I'm thinking is breadth first search through the binary tree, right? And then for each node, we'll actually do a depth first, well, through the binary tree, right? That being the case, we'll have 2 nodes to start with, right? An L and an R, right? We'll say LR, right? And we'll get the DFS of L, right? And a DFS for R, right? And we'll just check. We'll just say, and I guess we can shorten this, right? And just say if, and this is actually very small, very small. So if we just say if the DFS, right, of L, and then we could just actually, the math.absolute value, right, of the difference is greater than 1, right, then they are not height, this is not a height balanced subtree, right? In that case, we would return false and keep going. So I feel relatively confident about this. Let's try and implement it. We can do an iterative breadth first search by starting with the queue, which will start with nodes root.left, right, and root.right, right, and we'll iterate while our queue.length, right, is not empty, right, and since it's not empty, right, we want to pull off the 2 nodes that we want to compare heights for, right. To do that, right, we're going to want to first say node 1 equals q dot shift, right, and then just for the sake of continuing what we're going to continue, we're going to need to push on continuous nodes to continually breadth first search through. That being the case, we're going to push on to the queue, and we can actually just get that second node first. So we'll take those first 2 nodes off. Then we're going to push node 1 dot left, right, node 1 dot right, node 2 dot left, node 2 dot right. So we're pushing all of those onto the queue because we're going to go through it later, right? Now you want to breadth first. This is our BFS up here, right? Now we actually want to, we have our L and R nodes. Now we actually want to do our DFS, right? So our DFS, we're going to say, we're going to call it calc depth. It's going to take a node, right? And it's going to return a number. The further we can go, we're going to add 1 to it, right? And then as soon as we can actually, now we're actually going to have to pass in a number, right? And so we'll say n1 depth equals calc depth, right? Pass in node 1 and start at 0, right? And we're going to say if the node, right, is null, then we're just going to return num. The depth is 0, right? Otherwise, right, we want to pretty much calculate the depth, right? So that's going to be calc depth again, I believe. So imagine we're here with 3. Let's do a better example here with 1 and 2, 2. We got the second left node of 1 in our hand right now, and we're calling calc depth on 2 right now. All right, so we're calling calc depth on 2, and we go to 3, right? So it depends, right? Where do we want to go? So we actually want to take the max. So it's not only left or right. We want to take the max, actually. Maybe what we'll return, actually, is the math.max of calc depth node.left, right? Starting at number, right, and going to the calc depth of node.right, going to number. right? But when do we return? We return when we get to the number, right? And so since we got here, we're going to want to add 1 to it. I'll make this a bit wider just so it's easier to see. And so let's just try and run that, right? So we have 1, we're going to have push both nodes onto the queue, we're going to have 2 and 2, or we're going to pull both off, right? We're going to say, hey, calculate the depth of this node 2. I mean, this node 1, which is technically node 2, right? So we're going to do calc depth. Well, calc depth of the node 1, right? It turns out that it is not, oh yeah, of node 1, right? So it exists, right, which is 2. So we're going to calc depth of node.left, right, plus 1. So now we're going to push a call of calc depth onto the stack. We're now going to have a depth of 1, right? But node 3, right, isn't empty, right? So we're going to now push another call of calc depth of node.left plus node num plus 1, which is going to be a depth of 2, right? So now we're going to be at 4. 4 isn't null, so we're going to push a call of math.max of 3, right? And this 3 is going to go to 4. Yeah, it's no, it's 3, which we're going to have num plus 1, which is 3. Go left, which is null, and then we're going to have not node, right, which is going to be, it's going to return 4. It's going to go right, right? Right is null, so it's going to return num plus 1. Oh no, yeah, so it's actually going to return just 3. And then we're going to go back up here. We're going to return 4, right? And then we're going to go here, and this is actually going to give us 3, or yeah, 3, I believe. And the max of 4 and 3 is going to be 4. We're going to go back up here. We're going to have 4 and 2. It's going to be 4. Then we're going to have 2, which is going to be 1. And so 4 will be greater. If we do 4 minus 1, it's going to give us the absolute value of 3, which is going to be greater than what we want. And so I think this could work, actually. And then we'll return false. And then we can just pretty much keep going through and check every node, basically. And we need to change DFS to calc depth. I'm also noticing that general function names are better because your approach changes throughout, and then when you don't change the function names as you work through it, it gets really confusing. So we actually don't need n1 depth since we're going to be calling depth first search here and there. And so if we make it all the way out here, we can return true. So let's try that. So we have 19, 19, and 31. It's my bad for not updating these names. 31. I have L and R. L and R don't even exist. What I mean to do is node 1, node 2. Oh, and it expects 2 arguments, right? So both of these are going to start at 0. I see, right? And our node could be null, right? Because we can push nulls on. In that case, we want to be cognizant of values that don't exist, right? If that is the case, we can actually so we should be good here. So something is going wrong here. If we do a depth first search of node 1, node 1 is going to be, let's just start with 3, right? So we have 9 and 20 in our queue. We take the 2 off the front, which is 9 and 20, right? Then we push on null, null, and 15, 17 onto the queue for later processing. Then we do if the math.absolute value of DFS of node 1, which is 9. So let's do a DFS for node 9. If it's not of node 9, okay, so 9 does exist, so we're going to do the max depth of node.left, which is null, right? We go into there, we return 1, right? We go right for it as well, we return 1. The math.max of 1 and 1 is 1. Right, so we actually get 1, so we have a depth of 1, right? And then we have a DFS of node 2, which is 20, right? So how do we calculate 20? Well, to start, we're going to start at 20, right? DFS of 20, 20 exists. So we're going to do the math.max of DFS, right? So we're calling it for 20. 20 exists, so we're going to do DFS of left and right plus 1. So we're going to 15 first, right? And we're actually going to start at value 2, because at 20 we started at 0. Now we're going to start, we call it for 20, right? The node does exist. So we do num plus 1 is 1. So we're going to go into 15 with the value of 1. Right, we're going to try and go left from 15. We can't, so we return 2, right, and we return 2 as well for 7. And if we do math absolute value of 1 minus 2, we get 1. So I feel like this makes sense, but the time limit is probably crazy since we're doing a breadth first search. Well, let's see if we can save our answer, right? So there's no reason to recalculate trees we've already been through. So let's create a map, right? And this map is going to store a value of basically tree node to depth, right? And we're going to say DFS gets the value. We'll also get map passed into it. And we're going to allow the map, right, with a tree node. It's going to be a map with a tree node for a key, but a number. So they said that all the values were distinct. It didn't say all the values were distinct, so let's say a number for that value. And then we can add map to all of these calls. Right, and so the first thing we're going to have is if map.has node, right, then we're just going to return map.get depth for that node. I wonder what's happening here. So I'm just going to do console.log q and then return null. I just want to see what q looks like here. I actually don't know if you can do a q.push like this. So that could be part of the problem. So for 3, 9, 20, they take off 9 and 20, and we push on null, null, and 15, 7, which makes sense. So what if I print the DFS of node 1 going from 0 including map? What do I get? I get a depth of 1 because node 1 is 9. Now if we do node 2, we should get 2. So we do get 2. So I'm curious as to what the issue could be. Oh, I have to set it. Oh my god, what am I doing? To use the map, you actually have to set it. So we're saying map.hasNode, right? And so when we're returning the number, we want to do map.set. Not the node that we're currently at, though. It would definitely be it would be right here. We'll just say const depth is that, and we'll say the map.set node depth and return depth. I should have removed the console.log. I'm also not certain that you can actually even use a tree node as a map value, because that doesn't exactly make sense to me. So let's say if we print, and then we'll return null just for the sake of debugging, node2 0 map, and at the end when we set the map, let's just allow us to print the map. I know we get a fake true value here. Oh, so it does actually let me, wait, no. 2015 17 equals 2. Yeah, you can't set a value like that. And you, if only I could do like a reference thing. Let me check something. I wanted to check if you get the memory address of an object in JavaScript. You cannot do that. We also have no guarantee, which we can see here that the values of nodes are distinct. That being said, I think the approach where you save your answers is not going to work. So I have 2, 2, 3, 3, 4, 4. So I think we need an approach So let me see something. Let's just say D1, right, equals this depth first search. Right, we'll just say D2 equals, right, you know, node 2 starting from the map. So D1, right, minus D2 is greater than 1, right? And we want to return false. But I want to see for node 1, right, depth is this, and for node 2, the depth is this. Guess I should have returned. I should have clicked return. I mean, I should have put. I just want to see on the first run what I'm calculating. I should be able to walk through this, so I'm actually trolling. And I'm still using the map. So there's so much wrong here. We can't save our answers, so we should remove this. Map setting nonsense. We'll keep the map in just for the sake of simplification. So for the node 9, right, we get a depth of 1. For the second node, we get a depth of 2, right? And so we're fine. So what's going on the following iterations that is giving us so much trouble that we're exceeding the time limit? Right? So at the same time, I'm going to print my queue. So my queue has null, null in it. And do I do a depth first search for nulls? I don't. I just return the value. They're the same. And then we have 15 and 7 right in the queue. So you'd have node 1 dot left, node 1 dot right, node 2 dot left, node 2 dot right. So why are we running out of time? Is it because there is a faster solution? Oh my god. It's because oh my god. It's because we're not skipping trash. Because we're not skipping. So I'm saying safe navigation operator left, and so this is outputting an not a null, an undefined. But when I'm pushing dot left, that is actually just undefined, right, on null. So what I need to do is, well, what if the values don't exactly match up? Oh man, did I literally just, So we have node dot left, node dot right. Have D1 and D2. Now let's just say 9 has a node for left, doesn't have a node for right. How do you calculate that difference? We could do node 1, right, then DFS. Otherwise, 0, we could do the same, node 2, if DFS is 0. I don't think that stops us from adding values that don't exist, though. So we go to 3, then we go to 9, we do a DFS for both, we're good. Then we go to 9, we pull 9 and 20 off, and we push node dot left and node dot right, maybe the key, there's node dot left and node dot right, maybe we only want to push if they exist. So let's try pushing if they only exist. So I don't think the solution is this weird branching depth first search here. At the same time, let's do it after we check to simplify the problem. Well, no, I think it's okay. I think it's okay to push non-existent ones. I think we just need something to filter out that process. Because what if, you have a node here that doesn't exist, right? And a node here that does exist. The difference would still just be 1, which is fine. The problem seems to be we only want to depth first search if the value actually exists. That being said, I see what I'm doing. We only want to push, these values on if the node itself actually exists. So what we need is something like this, which we could duplicate and say if node 2, then you want to push on these values. Then we could delete this. We could delete all the map nonsense. And oh, it's so bad. I literally, that's frustrating. No, it is what it is. I literally fried this problem, and then I literally spoke, when we started this recording, I said it's important to double check your assumptions, and I assumed I knew exactly why the code was looping on itself infinitely, and I didn't, and it was literally because of an infinitely undefined nature. And it's fine if one of the nodes doesn't exist. We just have to make sure that we don't push on children that don't exist onto the queue. So that was my bad. So let's see how they solve this. I mean, the time complexity for this, we're doing we're visiting every node. I think there's no other way when you're doing these problems. Actually, I don't know, but I feel like if you have to double check the depth of every node and make sure that for every subtree that makes sense, you have to visit every node anyway. And I think we could have memoized this by making sure that each value itself, if we visited a node before, that we'll save the depth we calculated for, but at the same time, the way you iterate through depth first search is top to bottom. So we actually would never reuse any answers. So in that sense, it's a little bit silly. So let's just see how you're supposed to solve this. A tree T rooted at R is balanced if and only if the height of its two subtrees are within one of each other. Subtrees at each other also balanced. Therefore, you can compare the two subtrees' heights, then recurse on each one. They also make the same assumption that an empty tree is balanced. Height of root.left, height of root.right is greater than 1, return false. Else return is balanced. Oh, so they did, oh, this was a better idea though, 1 plus the max of both. I didn't max that, max of both plus 1. But interestingly, they're saying empty subtree satisfies the definition of a balanced tree if root equals null. That makes sense. Math thought abs of height, so root dot left minus height root dot right. I see. So they're saying, how about we just check if the root tree is if the root doesn't return differing heights. They're saying if the height of the root dot left and height of the root dot left, height of the root dot left minus height of root dot right is less than 2. So let's check. 1, 2, 3, 4. 1, 2, 3. We're good, right? So we'd return true. And root dot left is balanced. We check if it's balanced by iterating through the whole thing. Now, what does this isBalanced function do? Oh, they're literally calling it again. Height.root. For a node P at depth D, height P would be called D times time complexity of n log n. So tree is height balanced, height of trees are within 1, tree is not height balanced. So isBalanced is checking if the root is null, otherwise it's going to do absolute value of height dot root dot left minus height root dot right. So height roots of left just takes the max. Tree is not height balanced. IsBalanced root dot right. Why isn't this balanced here? It's unclear why this is unbalanced. This tree looks balanced to me. How do they do bottom up? Let me see if I can absorb this a bit more. First, you define a function height such that any node. I don't think I understand a height balanced tree. The balanced tree definition hints at the fact that we should treat each subtree as a subproblem. The question is, in which order should we solve the problem? Given the definition of a balanced tree, we know that the tree T is not balanced if and only if there is some node P, which is in T, such that height, the absolute value of height sub P dot left minus height sub P dot right is greater than 1. All right, so we have a node going slightly further. But then down here, we say that the tree is not height balanced. Does there exist a node such that the length is longer than the other? 1, 2, 3, 4. 1, 2, 3, 4. There does not. Yeah, I'm very confused. I don't understand how this is not a height balanced tree. Check if they have a height within 1. If they do, check if the subtrees are balanced. So my version does a top-down level. My version does a breadth first search through the binary tree, and then for each node, we then check their depths. So we go here, calculate the depths. Go 1, 2, 3, 1, 2, 3. I don't get it. I don't see how this is not height balanced. Maybe the Python solution will make more sense. Compute the tree's height via recursion. Def height. An empty tree has height of -1. If not root, return -1. Return 1 plus max.self.height root.left self.height of root.right. An empty tree satisfies the definition of a balanced tree. If not root, return true. Check if subtrees have height within 1. If they do, check if the subtrees are balanced. Subtrees are balanced. Self.height of root.left minus self.height of root.right is less than 2. Yeah, I don't understand, but I think should we count that one as a fry? I don't know. I think we just got stuck on a silly bug, but technically our original, I check if my solution, I mean, you don't really get to know when you first submitted it, so it is what it is. We'll do an older problem now. Do best time to buy and sell stock. We have function max profit, which prices an array of numbers. We're given an array of prices where prices sub I is the price of a given stock on the ith day. Given an array of prices where prices sub I is the price of a stock on the given stock on the ith day. I want to maximize your profit by choosing a single day to buy one stock, and choosing a different day in the future to sell that stock. Turn the maximum profit you can achieve from this transaction. If you cannot achieve any profit, return 0. So basically, we want to buy low and sell high. If we buy on 1 and sell on 6, it looks like we get an output 5 because we have to return profit minus our buy-in minus our buy-in minus our sellout, or our sellout minus our buy-in. So we made a profit of 5. In this case, no transactions are done and the max profit equals 0. So there's no day you can buy and sell and make money. That being said, the solution here would be 0. So I think what we can do is just keep a running min of the lowest we could buy the price for, and then on each day we'll keep a running max of the profit for which we could have sold our lowest buy-in for. So what that means is iterate over prices, right? We'd have a profit variable. Since we have a profit variable, right, we also want to keep track of our lowest buy-in, and these two variables will allow us to get to the end. So if we iterate over prices, we want to take the minimum so far we've ever seen of lowest buy-in and the current value. If we start, we can see that value is going to be 7, right? And so it is what it is. We'll say lowest buy-in equals math.min of lowest buy-in, right? And, price is sub I basically. So it's going to be 7. Our lowest buy-in is 7, right? But also our maximum profit that we can get is just going to be the math.max of profit, right? And the current value we're at minus our lowest buy-in. So that's going to give us 0 in example 2, right? We're buying on day 7, and our lowest profit is going to be our highest profit is going to be 0, right? Then our lowest bind is going to be 6, right? And then we're going to try and sell it on the same day. It's going to give us 0, right? Then our lowest bind is going to be 4. We're going to try and sell it on the same day, so on and so forth, and end up at 0. And no matter what day we buy on, it's always 0 as our profit. So we can see, right, if we start here, we'll say 7 is going to be our lowest bind, right? It begs the question, what should lowest bind start out? Since we're taking the min, we want it to start at infinity, right? And profit can just start at, profit can honestly just start at 0. So if we take our first example, we'll have 7 for our lowest buy-in, right? Then we'll try and take the max of our profit, which is 0, right? Or prices sub I, right, which is 7, right, minus lowest buy-in, which is also 7, right? So our max profit so far is going to be 0. Go to the next number. Lowest buy-in is going to be 1, right? And so we're going to sell on the same day, and our max profit is also going to be 0. Our lowest buy-in is either going to be 1 or 5. We'll keep 1 and see what our max profit can be. It's going to be 4. So that looks good. Then we go to 3, right? Our lowest is still 1. Max profit we can make here is 2, right? 4, what's greater between 4 and 2? 4. We get to 6. We do 6 minus 1 is 5. We do 5 is greater than 3. We take 5, and 5 is still greater than 3. So we can implement this now. We'll just say let profit equals 0, let lowest buy-in equals infinity, right? And we'll just iterate over the prices. We'll say let I equals 0, I is less than prices, and we can honestly make it even simpler just by doing const price of prices. We don't necessarily need the index. We want to make sure to return profit here. We can just delete these comments. Let's say lowest buy-in was the math.min of lowest buy-in or price. Our profit is the max of profit or price. So that looks good. We're not getting any light ups. That must mean I messed up here. And let's see what we get. We had a variable mismatch. Make sure you don't have any more prices, profit. So that looks good. And so this makes sense, at least to me. So the time space complexity would be linear time, so they're just iterating over the prices array with constant space. So let's try another problem. We already did balanced binary tree. Let's try implement Q using stacks. After this one, I think we're just going to do old problems. We're going to have class. We're going to have a class myQ. Okay, implement a first in, first out queue using only 2 stacks. The implemented queue should support all functions of a normal queue: push, peek, pop, and empty. Implement the myQ class. Void push pushes element X onto the back of the queue. Pop removes the element from the front of the queue and returns it. Peek returns the element at the front of the queue but doesn't. Returns the element at the front of the queue but doesn't remove it. Empty returns true if the stack is empty, false otherwise. You must use only standard operations of a stack, which means only push to top, peek, pop from top, size, and its empty operations are valid. Depending on your language, the stack may not be supported natively. You may simulate a stack using a list or deck, as long as you use only a stack standard operations. Interesting. So they want us to implement a queue with 2 stacks. So if a queue is kind of like a line, right? If you get in at the front, right, people enter from the back always, and they get handled from the front. A stack is the opposite. If you're the first in line, you're actually the last in line. That being said, what are the common intuitions? What is the intuition that, I guess, what's the impetus for this problem? If we imagine a stack to implement a queue, right, we can only add to the top and remove from the top as well. So how do we make sure that if we have a group of plates that we could take out from wherever we wanted, if we stack them in a stack, how can we process them in the order that they were given to us? We'd have 1, 2, 3, 4. But we can only use a stack. My intuition is telling me that if we use 2 stacks, we could choose a middle point, I guess. And depending, with 1 stack, we could take elements from the top off. We take elements from the top. So let's just try and write this down. We'd have 1, 2, 3, 4, 5. This is the regular stack. This is the regular queue, right? And 1, 2, 3, 4, 5 is the order they would be handled in. But if we take that same, if we take these numbers in a stack, we'd handle them in reverse. So we can't actually get to numbers specifically because that would be outside of the operations of a stack. So what if we used a midpoint? If we used a midpoint, we could have 2 stacks. Basically, do something like this, right? But we'd have 3, 2, 1, and then 5, 4. So if we take our midpoint, what if we say this one is for elements that are greater than or equal to 3, and this is for elements that are less than or equal to 3. Now if we do that, we'll have, we actually want to swap these. Oh no, so if it's greater than or equal to 3, basically we'd have to insert the numbers in reverse order. So when we add a number, we have to go 1. So okay, 2 stacks. Interesting. Out, we have push. We're going to push it on to the end. Implement queue using stacks. Using only 2 stacks. This is basically stacks versus queues. So we could do, if you push an element onto the end, that's fine. Except when you pop, you just have to go all the way down to the bottom. Set that value. Basically remove that value, but we're saying with the stack, I guess you could, if you use a stack, for example, if we added 1, 2, 3, 4, 5, forget the double stack intuition, we could just add them to the stack. and when we want to push a value onto the end, right? So if we push this, if this is the orders that they were added into the queue, right? We could take an element from the front or the end, right? Now, if this is the stack, right? When we push, we'd still add one towards the end, right? When we do pop, we want to be able to remove one from the front. To do that, we could just empty out all the elements except one element. And to do peak, I mean, all the operations, peak would not be linear, peak would not be linear time, pop would be linear time, and push would be constant time still. I think this means we probably also have to make sure so it looks like, are they assuming that our solution is going to be allowed to be more than linear time? Because if it can be linear time for an operation such as pop or peak, then we could just go, like we said, go down to the bottom, because we get peak, push would be free, empty would be free, we get pop and peak in linear time. Actually, we could get pop and peak. What if we treat the second stack as always the front of the array, of the queue, I guess. If we did that, we could have two stacks like this. One would be the front and one would be the rest, basically. And in this way, only the first operation so let's say we add one, right? We add one to the front, right? Well, now our front stack is filled, so we'd add 2, right? Then we'd add 3, and then 4. And then if we did pop, we get that in constant. Oh, we'd only get it constant time once. So it actually doesn't make sense. I don't think you can get. Well, pop isn't constant time. I mean, yeah. Well, yeah. Wait, in a queue, pop already isn't. It depends on the language, I think. So if you're moving an element from the front, then you have to shift all the elements forward, so it ends up being linear time anyway. If that's the case, then we would technically mimic it by having this front element, right? Where if you do a pop, right, you would go all the way down, pretty much check the first element in the front, right? Return that element, then also take the end element, the next end element, and put it in the front spot. But let's just do the basic stack version. Let's just do stack, which is going to be an array. And if they want us to push, right, then we're just going to do stack.push x, right? If they want us to pop, well, this is the time where it actually gets a little bit complicated. We would actually do const last, right, should be equal to let last equals null. So you would go all the way to the bottom, and how would you go to the bottom? If you're going to the bottom, then actually I'm noticing. So if you're already going to the bottom, then if you're going to the bottom, you could just reverse one of the stacks, and if you keep reversing them, so actually if we take the original we had earlier, 2, 3, 4, 5. Then we'd have 2 stacks, right? If they pushed 1 onto the stack, it'd be empty, right? If they pushed 2 onto the stack, if we put in the other one, actually no, what if we put into this one? And they push 3, when they want to peak, we could just do, we want to get the first element, we could do the first peak, which would actually go all the way down to 1, into which we could return the same outputs but in reverse, and then return the first element, which would be 1. But if they want to do pop, we do the same thing except remove 1 from both. But then when they want to do pop, we can just remove 2 from here. Nah, that doesn't make any sense. So if we have the stack, let's go all the way to the bottom. We need to get 1. So we basically we'd have last equals 0. Right, and we could just copy the stack. Now, this is a list, so you can do that, but you have to go all the way bottom to the stack. So you do while stack dot length is greater than 0. What should we return if it doesn't? All calls to pop and peek are valid, so we'll just ignore it. While stack dot length is greater than 0, we want to do temp dot push. Like go all the way to the bottom. Do that, we would just pop all the elements off the stack. Once we got to the bottom, we'd keep then we'd push all the stack dot pop, and then we would push val call it, we'll say last and then we could return last. So if we had this, we'd say, well, stack dot length is greater than 0, it's 5, so stack dot pop last equals 5, 4, 3, 2, 1. While stack dot length, we'd be out here, so we could just return last to push them all onto the 1, 2, 3. We'd have 4, 3, 2. So we'd actually have it in reverse. 2, 1. Wait, huh? Push 4, 3, 2, 1. So it actually be, I don't know if you can use other I'm trying to strictly use stacks without using any other arrays or anything like that. So maybe I'm taking the implementation too seriously. That being said, we could do this with recursion by chance. Nullify elements by setting them to null. So let's just say we have this in the stack with 3, 4, 5. How would you go deeper? Let's just say we'll create another method called reverse, which will take a stack and just reverse it, but also return a number. The way it does that is by having an inner stack and does while reversible dot length is greater than 0. This is let val equal reversible dot pop, and then it pushes this inner dot push val, and then we can return inner. So what does that look like if we had 1, 2, 3, 4? 4 would be greater than 0. And then we'd say value equals reversible dot pop. We pop 4 off. Then we'd push 4 onto here, right? The length would now be 3. We'd pop 3 off, push 3 onto here, right? Then we'd have 2, pop 2 off, push 2 onto the inner. Then we'd have 1 left, pop 1 off, push 1 off the end. And then when we want to pop, we can just say reverse equals reverse of this dot stack, and then we can just return reverse reverse this dot stack. Then we can return reverse this dot pop, then set stack equal to this dot reverse, and when we want to peek, right, we can say const reverse equals this dot reverse this dot stack. Oh, we know we'd say this dot stack equals this dot reverse, and then reverse this dot stack. We'll just call const popped equals reverse. So we reversed our current stack, right? Reverse dot pop, right? And then this dot stack equals this dot reverse. We can return pop. We want to peek or reverse the stack and then return this dot stack. So this, or no, reverse sub reverse dot length minus 1, and if it's empty, we'll just say return this dot stack length equals 0. So if we want to peek, we reverse the stack and then just get the last element in it, and we want to pop, reverse the stack, pop the last element off, keep a reference to reverse the stack again, and return popped. Oh. Want to push, we just do this dot stack dot push. It's reversible, this dot reverse. It's really undefined. So if we push 1, push 2, and then peak, we should get 1, which we do. If we do pop, we get undefined. So we should reverse this dot reverse this dot. So reversible dot length is greater than 0. Let val equal reversible dot pop. Turn inner. And then we want to pop it. We say this dot reverse. This dot reverse, reverse it again, right? Pop the element off the end. This dot stack. Oh wait, this dot reverse, this dot stack is by reference. So if we copy, oh no, well it's a stack, so you can't do that operation. We would just copy reversible. Copy equals dot pop. So we say this dot reverse, reverse the stack, we get reverse. So reverse dot pop, and this dot stack equals this dot reverse the version that's pop, and then we should be able to return it. Interesting. So a lot of reversing. Maybe we could reverse, if we reversed it once, it depends. If you wanted us to use 2 stacks, I think what you can do to optimize the reversing is just keep 1 stack and then keep another version of it that's actually that version in reverse. How do you optimize that? You push onto the stack. When you pop, when you push or pop, this is what we have. So push is constant time, but pop is linear time. Pop is constant time, right? Because if we're going all the way down there, we might as well save the value so we can always peek it. So our pop is actually 2n. So is our push is constant time, but our pop is linear time. I think you could swap these and get the same output. It ends up being that push is a better linear time since when you're on your way down, but since you're here on reverse actually you can actually do the same thing. If we just do front equals, can we make sure all the values are positive? Right, so the values are always front equals 0, and on our reverse, on our way down, actually reverse is not cognizant of what order it's in. Only when we push do we know what order we're going in, basically. Actually, I don't know if I understand. Pushing element 3 to the queue. Right. To remove the element in front of the queue. It's the first inserted element in the stack. This one. Oh, I see what they're saying. He was shuffling it back and forth. Then how do you do peak? S2, then you just pop S2. So S2 is empty and S1 is not empty for the elements. S1, S2, and you just pop S2. Well, why don't they push them back? Because when you do push, this 2 would be full now. If you have pop, there's a lot going on there. My stack and yes helper. If helper is empty, then num equals helper dot top. Helper dot top return num. Now the stack is empty. Helper dot push one. This way, if not helper, so you have helper in my stack. If you pop an element, helper in my stack, helper is empty in this stack. So let's push an element, push it onto my stack. And if the helper is not empty, helper is empty while stack is empty. Helper dot push isn't empty, then you pretty much flip all the elements. Push all the and then you do helper dot top, helper dot pop. Okay, well if helper is not empty, then helper dot top, helper dot pop, return num. You can keep your element. Then when you peek, helper dot top. And while the stack isn't empty, move everything into helper and then do helper dot top. Then we push. Let's push onto X. So we have my stack has X and it's not empty. We push. I see. I see. Interesting. Interesting. I don't know if we tried balance binary tree. Keep that one open. Solved. Went Q with stacks. So we just did. And I guess we'll just close. So your function is anagram. We have S, which is a string, and T, which is also a string. So given two strings, S and T, return true if T is an anagram of S and false otherwise. An anagram is a word or phrase formed by rearranging the letters of a different word or phrase, typically using all the original letters exactly once. So anagram is an anagram of nagaram, and the reverse is also true. For this to be true, then for every element in A, we have to be able to match it to T. So one way to do this, to start, we know that S and T consist of lowercase English letters. And one way to start for certain is to know that if S dot length is not equal to T dot length, then they're not anagrams at all, because you need to be the same length to be an anagram. Additionally, we know that if for every letter in in S, it matches up to T, then it is an anagram. So another way to do this would be to sort the letters. If we didn't want to use any space, or if we want to use linear space, or I guess S log S plus T log T time to sort these strings, but we can do a constant space solution with a map And the way this works is we'll load letter, occurrence, pairs into map of S, and then from there we can just iterate through T and make sure that T zeroed out S. Decrement letters in T from S map, right? And then we have to iterate over map, make sure, right? Make sure all occurs equals 0, and if they all equal 0, then we know that S built up something, and then T removed it with everything that S added, and thus they would be anagrams. So if they make it all the way out here, we'd return true. So to load letters and occurrence pairs into the key value map with S as the starting string, create a map. We'd want to map, our types would be of string to number, right? Then we could do for const car of S. We could have a value, and we'd say if the map has the value for a character, and then get it. Otherwise, set it to 0. And then we could set the maps key, which would be the character, equal to value plus 1. Then we could decrement letters in T from S's map. To do that, we'd have to iterate for const car of T. And what we'd have to do is basically subtract all the values from for each character in T. If the character in T exists in the map, and we want to subtract from the occurrences, right? So if map.has character, right, then we'll do some work. But otherwise, if it doesn't, we want to return false, right? If a character exists, if T has a character which S doesn't have, then it's automatically not an anagram. Then here we can set map.setCar to value minus, to map.get car value, right, minus 1. And then in the final case, we would iterate over the map, and we would do for const, and we don't really care about the keys. We just want to make sure all occurrences equal 0. So for all occurrences of map, right, if occur is not equal to 0, we want to return false. So let's check if this makes sense. So we'd have do S and T's length, are they equal? They are. For the map, we have a key value pair of map to number, iterate over every character in S. We'd have const value if map has the character, right, get the value for the character. Otherwise, set it to 0. We'd have 2A, 3A, 1N, 1G, 1R, 1M. Then decrement letters in T from S's map. So for const car of T, check if N is in the map. It is. We'd set N in the map equal to 1 minus 1, which would be 0. And then keep going, keep going, keep going. Some would go negative, which is fine, which is not fine, but we'd find that in the second iteration through here, right? And here we could see that if we check all the occurrences, they should all be zeroed out. But for rat, we'd set R1, A1, 2-1, and then in car we'd set, well, actually we'd fail right here because it's not even in the map. This would be S plus T times, since we have to iterate over both with constant space, since S and T always consist of lowercase English letters, and our map for any arbitrarily large string will only ever use 26 value keys to map to values.